So we were discussing one-dimensional steady-state heat transfer along a rod, that is extended surfaces, or also called as fin. So far we have derived governing differential equation for this condition, for uniform cross-sectional area fin in the form of straight rectangular fin and circular profile fin. And equation number 4, 5 and 6 are the governing differential equation. In equation number 6, m is called a parameter which is given as m is equal to square root of Hp over Kac. H is convective heat transfer coefficient, P is perimeter of the fin, K is thermal conductivity of the material of which the fin is made of, and AC is its cross-sectional area. Equation 6 is nothing but homogeneous linear homogeneous second order differential equation, and its solution is given by so its solution is given by theta, that is excess temperature at any location x. It is combination of complementary function plus particular integral, and it is given as, after solving, we at this point of time we won't bother about how this solution is arrived. In mathematics we have done all these things. Let's say this is equation number 7. And theta x can also be represented as Tx, that is temperature along the length of the fin at any distance x from the base surface minus T infinity. So basically the significance of equation 7 is, with the help of equation number 7, if I put the value of x anything between x equal to 0 to x equal to L, that is length of the fin, I will get the temperature at that particular distance. But what is the problem with this equation 7? It consists of two unknown constants whose value is to be determined. M value is known to me, X value is known to me, C1, C2 are the unknown constants whose values are to be determined. And in order to determine the values of these two constants, sorry, C1 and C2, we must have boundary conditions. So on Friday, we have discussed case number 1, that where, what was the case? We have found out the expression for Tx for a heat dissipation from a fin attached to the base surface of infinite length. Okay. So that derivation is there in different sheet. I will make it available to you. So for infinitely long fin, that is when its length tends to infinity. If I want to find out the temperature distribution, I could get in this way. Theta is nothing but theta x. It can also be written as Tx minus T infinity over Ts minus T infinity, and it comes out e to power mx, and in terms of hyperbolic function, it comes out sine cos of hyperbolic mx minus sine of hyperbolic mx. So see, in this equation, the only unknown thing is x. M we can calculate. Once we know the value of H, P, K and AC, I can calculate M. Base temperature will be known to me. Environmental temperature will be known to me. You go on, put the value of X, you will get the value of Tx. Okay. And what were the boundary conditions in this case? At x equal to 0, that is on the root of the fin, Tx is equal to Ts, and at x equal to infinity, that is at the tip of the fin, Tx become T infinity. These were the two boundary conditions we had. Okay. In terms of excess temperature, I can also write them and excess temperature for surface. So what we did actually on the Friday class, using equation number 7 and using these two boundary conditions, I got the values of C1 and C2 constants. Then I put the values of these C1 and C2 constants in terms of known value once again into equation 7 and rearranged. I got this expression. Okay, so this was the case 1, that is heat dissipation from a pin fin of infinitely long length. Now today we are going to discuss case number 2. Before this, let me allow some students to enter. They are waiting for my confirmation. Now case number 2, heat dissipation from a fin insulated at tip. Now this can be case number 2. So let us first draw the schematic of this. Let us consider there is a fin of finite length. Okay, heat dissipation from a fin of finite length L and insulated at tip. What does it mean? At x equal to 0, this is the root of the fin. So this is nothing but base surface at temperature Ts. The fin is having finite length L. So at x equal to L, what we are assuming here, We are assuming this fin is insulated at this tip. Okay. Now, if I want to draw the temperature variation, this is the Tx, and on the x-axis, this is the length of the fin or distance from the base surface. So environment temperature is going to remain the same. It is not going to change everywhere. But the base wall temperature, as here the base wall temperature and temperature of the fin at the root will be same. That is equal to Ts. But as the heat is conducted into this fin along the length of the fin, and heat is also convected from the fin surface, the temperature of the temperature of the fin goes on diminishing as we move away from root to the tip. So this will be decreasing. So this will be the variation of temperature along the x direction for fin with insulated tip. So title of this figure will be insulated tip fin. Now those who are joining late, they are requested to please join beforehand. It creates a lot of disturbance for me. Switching from OneNote slide to the Google Meet slide and then admitting and then allow you to admit is quite irritating for me. Okay, so now this is the case number 2. Now what will be the boundary conditions? Under such condition also, I want to find out the variation of temperature of the pin fin in the x direction. So what will be the boundary conditions? The very first boundary condition, as you can see here, at x equal to 0, that is at the wall surface or at the root of the fin, temperature in the x direction will be equal to base surface at x equal to 0. In terms of excess temperature, it can also be written as Tx minus T infinity over Ts minus T infinity. This can be represented as theta x is equal to theta s. This is boundary condition 1 for this case. Second boundary condition, as you can see here, at x equal to 0, that is at this distance. At x equal to L, the fin is insulated. So there will be no heat transfer from the fin. And if there is no heat transfer from the fin at the tip, there will be no temperature variation. So what does it mean? Variation of temperature with respect to x will be 0 at x equal to 0, x equal to L. From where it came? From Fourier's law of heat conduction, we know heat transfer rate is directly proportional to temperature gradient. At tip of the fin, there is no heat transfer because of insulation. So temperature gradient will also become 0. This is the boundary condition number 2. In terms of excess temperature, I can write this as d theta x over dx is equal to 0 at x equal to n. Now we have two boundary conditions for case number 2, and we have the solution of the governing differential equation in order to find out the value of Tx, that is equation number 7. Now let us put these two boundary conditions for case number 2 into equation 7 one by one. So putting boundary conditions 1 and 2 into equation 7. Okay, so let us first put boundary condition 1 into equation 7. What I will get? At x equal to 0, so I will put x equal to 0 here. Theta x is equal to 0. So when I put x equal to 0, e to power 0 will be 1, e to power minus 0 will also 1. So what I will get? Theta x is equal to 0 at x equal to 0. Left hand side will become 0 and right hand side will be C1 plus C2. So let us do this. Theta x equal to 0. C1 into e to power m into 0 plus C2 into e to power minus m into 0. E to power 0 will be 1. So after putting boundary condition into equation 7, I will get the relationship. Oh, extremely sorry. At x equal to 0, theta x is equal to theta s. Please do this correction. Or C1 plus C2 is equal to theta s. At the base surface, temperature of the fin at the root is equal to base surface temperature. Let's say this is equation number A. Similarly, from boundary condition 2. Now what boundary conditions 2 says? D theta x over dx is equal to 0 at x equal to L. Got it? Now here, I cannot put the boundary condition directly. I have to do some simple mathematics. What is that? D over dx, an expression for theta x is C1 emx plus C2 over e minus mx at x equal to L will become 0. Because this is nothing but equation number 7. This is the value of theta x. Now differentiate it. I will get C1 m e to power mx minus C2 into m e to power minus mx, and if I put the value of x equal to L, this entire value will become 0. So m is common, I can take it out, it will become 0. It is not actually 0. If I take m common, okay, let me write what I want to say actually. C1 e to power, now I put the value of x equal to L, ml minus C2 e to power ml is equal to 0. Now m cannot be 0, isn't it? Because m is some parameter consisting of geometrical and thermal properties of the material of the fin and surrounding fluid. So m cannot be 0. So I can write from this analogy C1 e power ml minus C2 e power ml is equal to 0. Let's say this is equation number B. So what actually we did, we solved equation number 7 along with two boundary conditions for case number 2. That is heat dissipation from the fin with insulated tip. Now, I am basically interested in the value of constant C1 and C2. So, from equation A and B, if you solve these two equations, these are nothing but simple linear algebraic equations. C1 plus C2 is equal to theta S A, and C1 e power ml minus C2 e power ml is equal to 0, equation number B. So if we solve these two equations simultaneously to get the value of C1 and C2, I will get the value of C1. Now I am directly writing. I am not doing that in between derivation. Theta S over 1 plus e power twice ml and C2 I will get theta S over 1 plus e to power minus twice ml. So these are the values of constant C1 and C2. And as you can see here, C1 can be expressed in terms of ml theta S, which are known to me, similarly C2. So all the parameters here are known to me basically. Now, putting the values of constant C1 and C2 into equation 7. What is that equation 7? Once again, it is nothing but this. Theta x is equal to C1 e to power mx plus C2 e to power minus mx. What I will get? I will get the excess temperature at any distance x from the base surface. The value of C1 is theta s over 1 plus e to power twice ml. This is the value to power mx plus theta s over 1 plus e to power minus twice ml. This is the value of C2 and e to power minus mx. Correct? Now I have to do some arrangement. So e to power twice ml, I can also write it as e to power ml into e to power ml, like this, from the law of logarithmic. Okay, let me do this. I will avoid to write the direct results. Otherwise, you will get confused. So this way I can express the denominator. Now I take e to power ml common. So theta s over e to power ml. So what will remain here? Here I want 1. So it will become e to power minus ml. So e to power ml into e to power minus ml, it will become e to power 0, that is 1. And the second term will be e to power ml into e to power mx. This is the first term. In second case, theta s over, now I take e to power minus ml common. So the first term will become e to power ml in order to make it 1 plus e to power minus ml, and on the numerator side it is e to power minus mx. Simple mathematics, nothing great here. This is not engineering, this is mathematics. Okay. Now take this ml on the numerator side, so it will become e to power minus ml. So theta s into e to power mx into e to power minus ml. Again from the law of logarithmic, e to power ml plus e to power minus ml. I have rearranged this. Plus second term will become theta s. Upon taking this value to the numerator, it will become e to power minus ml into e to power minus mx, and this will be e to power ml plus e to power minus ml. Now once again from the law of logarithmic, what it will become? It will become e to power m x minus l over e to power ml plus e to power minus ml, plus second term will become theta s e to power minus m l minus x over e to power ml plus e to power minus ml. And this entire term on the left hand side is equal to excess temperature at any distance Tx. Theta s is common, I can take it out and I can take it on the left hand side. So theta x over theta s will become e to power m l minus x plus e to power minus m l minus x over e to power ml plus e to power minus ml. Now once again I have to simplify this. So let me recall the formulae. What are those formulae? Okay, those formulas are in different slides. So let me reproduce them. Cos of hyperbolic mx is equal to e to power mx plus e to power minus mx over 2. Okay. So same thing we are getting here. So can I write this entire term in the numerator in the form of cos of hyperbolic mx? Yes. Here x will be replaced by L minus x. So this entire term, numerator term, will become cos of hyperbolic m L minus x into 2. This 2 will be multiplied by this because we are supposed to get this value. And similarly, the term in the new denominator will become twice into cos of hyperbolic ml. Okay, so finally, what I will get? The ratio of excess temperature at any distance x over theta s will be cos of hyperbolic m into L minus x over cos of hyperbolic ml. And theta x is nothing but tx minus t infinity, and theta s is ts minus t infinity. So this way I can get an equation to calculate this unknown temperature Tx at any distance x from the base surface along the length of the fin for the boundary condition when fin attached to the base surface is insulated at the tip. So let me highlight this.
Sir,
Yes.
first equation wrong way, sir. E to power m x minus L है, sir.
Which one?
Sir, third one. जहाँ पर से
Okay,
wait
wait,
किया.
wait. Just a minute. This one?
Yes, sir.
Oh, sorry. This one?
Yes, sir. Yes, sir. X minus L, sir.
It should be.
X minus L.
Please, let me check. X minus L. Okay, this is e to power x minus L. Yes. Then this is e to power m L minus x. Isn't it? So if I take minus sign from here, oh sorry, it will be like this. Correct. Thank you for pointing out. Actually, same thing is there. Second term will be e to power m L minus x. Please. E to power m L minus x, and this will become what? E, if I take minus m common, it will become L minus x. Let me correct this for you. If I take minus m common, it will become L minus x. And this will be theta s e to power m L minus x. It is okay now. Actually, first term we will get from second term we will get from first part. So like that, now I can return it. E to power m L minus x, that is this, plus e to power minus m L minus x plus e to power ml. Okay, so this way it will become theta x over theta s is equal to cos of hyperbolic m L minus x over cos of hyperbolic ml is equal to tx minus t infinity over ts minus t infinity. Okay, this way. Now question comes to your mind. Is it necessary to remember all these formulae? What we derived for case number 1 and case number 2? So you need not to remember any formula. Neither the formula in terms of this ratio for case 1 or case 2 and formula for heat transfer rate by fin if it is infinitely long or if it is insulated tip. One more case is there. All these formulae are given in data book. After this class, you please refer your data book after 1 p.m. You will find all these formulas are given. Notations may be different, but the equations remain same. So no need to remember these formula at all. And these derivations are generally asked in examination. In the form, derive the governing differential equation for heat transfer through fin and deduce it for case number 1 or 2 or 3. Correct? This way you are supposed to solve this derivation. Now similarly, I am interested to calculate heat transfer from fin in second case. So once again, from Fourier's law of heat conduction, what is happening actually in the fin, heat is conducted from root in the x direction by conduction. So Q fin will be minus K into AC because this cross-sectional area of the fin will be normal to heat flow, and dTx over dx, and this is at x equal to 0. Okay, and this Q fin for insulated tip fin. In the similar tune, we have derived for case 1 as well. That derivation video I will be posting in Moodle. Now minus K AC d by dx. What is the expression for Tx I can get from here? If you rearrange this, what I will get? See, I am writing the value of Tx directly from here. It will be T infinity plus Ts minus T infinity into cos of hyperbolic m L minus x over cos of hyperbolic ml. And after differentiation, the value of x will be 0. So Q fin for insulated tip fin will be minus K AC. Differentiate this, T infinity will become 0. Ts minus T infinity is constant. It cannot be differentiated. Okay. Cos hyperbolic ml, this is also constant. Why constant? Because there is no variable. M is also constant, L is also constant. So we cannot differentiate it, and differentiation of cos hyperbolic ml will be sine of hyperbolic m L minus x, and this constant m will also come out. And in this entire expression, we are supposed to put x equal to 0. Now, please remember differentiation of cos hyperbolic mx will be equal to m sine of hyperbolic mx. This is the formula. Now simplify this, minus K into AC This will vanish, Ts minus T infinity. Now put the value of x equal to 0. So what it will become? It will become sine of hyperbolic ml, x equal to 0. So it will become sine of hyperbolic ml over cos of hyperbolic ml. After simplification, I will get the expression for rate of heat transfer from insulated tip fin will be, now m is constant, I can take it out, minus K AC into m into Ts minus T infinity 10 of hyperbolic ml. So this much heat transfer will take place from the fin attached to the base surface with insulated tip. Correct? Now, no need to remember this formula also. It is also given in data book. So this will be the rate of heat transfer from single fin with insulated tip fin. If there are n number of such fins are there, let's say 1000 fins are attached, then what will be the total heat transfer? The total rate of heat transfer from the fins? N into Q fin, insulated, this way. This formula is also given in data book. Correct. So this way I could derive the expression for temperature variation along the length of the fin in the x direction for fin insulated at tip and rate of heat transfer from such fin.